vortices, and now we have vortices also. Everything is as planned.
Thank you. So I want to thank the organizers for inviting me to be here. I'm very happy actually that I'm here, as opposed to transmitting this talk from Madrid. In particular, since it is 11 p.m. But there. And also I have to apologize to Nuno for betting about the number of speakers on that would speak on Sigma models. It was me. You want a beer? No. I accept it. Well, I hope I trust that vortices count, right, as Sigma models. I tried not to, but just to win. But I guess they do. Huh? Okay, no sabotage. So I will talk about vortices somehow in the presence of gravity. And this is joint work with Luis Alvarez Consul and Mario Garcia Fernandez. But before so these are vortices on Riemann surfaces. But before I do that, I would like to review a more classical theory of vortices on compact Riemann surfaces. And so a billion vortices. So we have a compact Riemann surface X, and we choose a Keller form on X with normalize the volume. We'll see, we'll normalize it to 2 pi, but any other normalization is fine. And we consider a line bundle over X, a holomorphic line bundle, and a section, holomorphic section of L. This is the Higgs field. And so the vortex equations, I regard the vortex equations as equations for a Hermitian metric, H on L, that satisfy this relation, where Fh is the curvature of the chain connection, compatible chain connection determined by the metric and the holomorphic structure of L. And so this is just a two form. Then, so what this lambda Fh means is a contraction of this two form with a Keller form. So it's just a smooth function. And the norm means the norm with respect to this metric, and tau is a real parameter. So these are the vortex equations. In-gauge theory, and especially in physics, is more familiar to study the vortex equations as equations for a connection A and a Higgs field, fixing first the metric on the line bundle and studying on a smooth line bundle, and studying for a connection and A and a Higgs field phi, such that phi is holomorphic with respect to the holomorphic structure defined by the connection, and then the similar this relation is satisfied. So this is an equivalent, totally equivalent point of view, but I prefer to take, because my focus is more, my work is mostly in algebraic geometry, to take this sort of more Hermitian point of view, sort of fixing the holomorphic structure and looking for a Hermitian metric. So in physics, this is these equations when you have the complex plane appears in the Gisborne-Landau theory of superconductivity, where Fh, the curvature, is the magnetic field, and phi represents the electron wave function, the density of Cooper pairs, right? So, and the Lagrangian of that theory depends on a parameter lambda, which in the Bogomolny phase, when lambda is equal to 1, the Euler-Lagrange equations of the theory are equivalent to the vortex equations, right? And now coming back to our situation, if we integrate the equation, by integrating, I mean that we just perform this operation, all right? Then we obtain a relation between the degree of the line bundle. This is the integral of the first-chain class. The curvature, of course, represents the first-chain class. The degree of the bundle, the L2 norm of the Higgs field, and the volume of X. And because of this relation, you realize, if we insist that phi is different than 0, and normalizing the volume of X to 2 pi, we realize that the degree of L has to be, in order to have solutions, has to be less or equal, the degree of L has to be less or equal than the parameter tau, if we want to have solutions. And in fact, the theorem is that the existence of solutions is to the vortex equations is equivalent to this condition. So it's a necessary condition is also sufficient. And if the Higgs field is actually 0, then just the Hodge theory ensures the existence of a metric satisfying that equation, and the parameter tau is not any value. It has to be fixed by the topology, is really the degree of the line bundle, the first chain class of the line bundle. If phi is different than 0, there are several proofs of this theorem. Steve Bradlow gave one proof showing that if you fix a metric and you consider any other metric which just differs from this by a function e to the u, a real positive function, then the u satisfies the Kasdan-Warner equation that was solved by Kasdan and Warner in an equation in Riemannian geometry, and this is how Bradlow proved the existence of solutions. I gave another proof based on dimensional reduction arguments, based on the dimensional reduction of Hermitian-Young-Mills equations. And I want to focus, to focus on that aspect, on that proof, just to remind or to tell you the main ingredients of that proof, because that will play an important role in the case of the gravitating vortices that I want to consider. So let me remind you the Hermitian-Young-Mills equations. The context that we have is now M, omega M is a compact Keller manifold of any dimension. And again, we normalize the volume. So the dimension we call N of this manifold. And we have a holomorphic vector bundle over M. So with this given objects, the Hermitian-Young-Mills equation is an equation, again, for a Hermitian metric on E, such that this satisfies this, where, as before, FH is the curvature. But of course, now, because we are in arbitrary rank, the curvature is a two-form with values in the skew Hermitian endomorphisms of E. And now, again, with contracting with the Keller form in M, what we get is, in fact, a section of this bundle of Lie algebras here. And we see that this mu here, again, is not any a priori is any real number, but in fact, we realize that this, again, is fixed by the topology. So by taking the trace of this equation and integrating, we obtain that, in fact, this mu here is what is called the slope of the bundle. This is the degree of the vector bundle divided by the rank, where the degree, notice here, is defined as a Chen class against the Keller form. Okay? So this is the Hermitian-Young-Mills equations, and they are very familiar equations when the dimension is 1. So on Riemann surfaces, it's a more familiar equation of flatness of a connection, or projectivity flatness if mu is different than 0. And if n is equal to 2 is the anti-self-dual connections or instantons, right? So it's a generalization of these two very familiar and important theories. And so the Hitchin-Kobayashi correspondence that I would like to recall actually gives conditions for existence of solutions to these equations. And the conditions come in the form of some algebraic geometric condition. So the algebraic geometric condition is called stability, and is a condition introduced by Mumford and Takemoto. It was a condition actually introduced by Mumford for Riemann surfaces, but generalized by Takemoto in higher dimensions. And you say that a vector bundle is stable if for every coherent subsheaf, E prime of E, the slope, which is the degree divided by the rank of the subbundle, is smaller than the slope of the bundle. And a relevant condition here also is that of polystability, which is that the vector bundle is a direct sum of vector bundles EI, all of them stable of the same slope. So that is the condition of polystable bundle. And so the theorem, the Hitchin-Kobayashi correspondence, says that, in fact, the existence of solutions to the Hermitian-Young-Mills equation is equivalent to E being polystable. And more refined is that if you want an irreducible solution, then the bundle E has to be actually stable. So this is a theorem that in n equals 1 goes back to Narasimhan and Seshadri almost 50 years ago. Next year, actually, we'll have a conference to celebrate 50 years of the theorem of Narasimhan and Seshadri. And was reproved by Donaldson in 83. And then for n bigger than 1 is due to Donaldson and Uhlenbeck and Yau. Notice, as I previously mentioned, that in contrast with the case of Riemann surfaces, when the dimension of the manifold is bigger than 1, both the equations and the stability condition depend on the Keller form. Okay, so what is the relation of the Hermitian-Young-Mills equations with vortices? So the relation is that, let's come back to the pair, line bundle and a section over a compact Riemann surface. And so I say that to this pair we can associate a rank 2 holomorphic vector bundle over the product of the surface cross P1, CP1. Yeah? So how is that done? So in fact, I say that that bundle, this holomorphic rank 2 vector bundle, appears as an extension of the line bundle, L pullback to the product, by the pullback of the O2 bundle on P1. And this is a very simple correspondence between these pairs and vector bundles like this. This is simply because of the following. If you compute extensions like this of vector bundles, but this line bundle by this other one, this is parametrized by the first cohomology group of this L tensor O minus 2, the dual of this, I mean the pullbacks. And just if you apply the Kenneth formula, you can express this as sections of L times H1 of this P1, right? And then there's another term which involves sections of P1 O minus 2, but that doesn't have sections, so it's only this. And because of Serre duality, this is isomorphic to sections, the dual of just holomorphic functions on P1, that is constants, right? So you show that extensions like this are indeed parameterized by holomorphic sections of L. So there is a one-to-one correspondence between pairs like this and holomorphic bundles of this sort. And moreover, that vector bundle comes equipped with an action of a group, the SU2. So SU2, so it has a lot of structure, that bundle. And so SU2 acts on X cross P1, acts trivially on X and on P1, realizing P1 as this symmetric space, SU2 cross U1, right? The standard presentation of P1. And the action of SU2 on this manifold can be lifted to the vector bundle, right? So it acts trivially on the pullback of L, and it acts in the standard way on this. This is a homogeneous, SU2 homogeneous line bundle. So it acts in the standard way here. And because the action of SU2 on sections of L is trivial, then E, this rank 2 vector bundle, is actually an SU2 invariant holomorphic vector bundle. So not only do we have a vector bundle like this, but in fact it has an action of SU2. The action of SU2 on basically CP1 lifts to the action on this bundle. And so we can now consider a SU2 invariant Keller metric on the product by taking just the metric, the Keller metric we had on X, and we pull back the Fubini S2D metric on CP1, conveniently parameterize, normalize, or with a factor depending on the parameter tau, where tau is positive, right? And we normalize the volume of the Fubini S2D metric to be 2 pi. So we consider this Keller form on X cross P1, and the statement is the following. Proposition is that the pair L phi admits a solution to the tau vortex equations if and only if the vector bundle 2 admits an SU2 invariant Hermitian-Young-Mills metric with respect to this Keller form. So the parameter here in the vortex equations is encoded here in the Keller form. And
if the curvatures had been opposite, then that would have been, your X cross P1 would have been conformally flat. When you've scaled it this way, is it half conformally flat, or is it still?
That could happen in some situations, but it's not necessarily the case that that they coincide having curvature Yeah.
So I don't know. Is it the case when the curvatures are different that it could be half conformally flat? I'm just wondering, is there anything in this that requires the twistor correspondence?
We are not using the twistor correspondence, right? But there are. It could be a situation. There's a situation where it could be conformally flat, half conformally flat, and you could just so that will impose a particular value of tau, right? And for which you can apply twistor methods. Twistor space is quite. But anyway, I mean, probably perhaps you know more about that.
Yeah.
But so we don't require. We have this moving parameter tau. And so what this is just, what this is just saying is that vortices on X are simply SU two-dimensional reduction of instantons on X cross P1. I mean, physicists are very familiar with dimensional reduction. This is a formulation more in the sort of bringing these ideas to more algebraic geometry, to the algebraic geometry of holomorphic vector bundles, right? But for physicists, it's a very natural thing. And in fact, this generalizes results of Witten, who obtained vortices on the hyperbolic real plane, starting, if you replace X by hyperbolic real plane, and taubes for if you replace X by R2, right? So this was the inspiration actually for these ideas. And so the proposition is that the bundle E defined by L is stable with respect to omega tau if and only if the degree of L is less than tau. So the stability of this bundle, which a priori a complicated condition, reduces in this particular case simply to this nice condition, the degree of L less than tau. So if you combine these two correspondences, you obtain the existence theorem that I was claiming before. So that's how I proved the existence theorem. So these ideas of abelian vortices have been generalized vastly to many situations, and many people have worked on them. I just want to mention some non-abelian vortices, and because of the relevance that they have for some other problem, which I'll mention. So the first situation is if we replace L, the line bundle, by a higher rank vector bundle, V over X. And so in that situation, and now we consider, as before, a section of this vector bundle, a holomorphic section. So Bradlow, many years ago in his thesis, at the end 89, 90, sort of introduced a notion of tau stability for such pairs, which was precisely the condition for the existence of solutions to a non-abelian version of the tau vortex equations. So it turns out that the correspondence that I mentioned before for line bundles also works for vector bundles. So I can, to a pair of a vector bundle in a section, I can associate, as before, a extension, right, of this vector bundle by, again, same construction, actually. And I proved that Bradlow's stability condition, that at the time it sounded a very complicated notion, which in the line bundle case is simply that the degree of L is less than tau, but in general was a very sort of technical condition, was simply the stability, the usual Mumford-Takemoto stability of this vector bundle. And in particular, this provided what was, in fact, at the time, the first construction of the moduli space of vortices, non-abelian vortices, or abelian for that matter, realized as a subvariety of the moduli space of stable bundles on X cross P1, something that had been very much studied because of Donaldson theory. So this is one situation. Another situation is that of, so this was generalized already, so what we call triples, a lot of work on them. And this triples is now realizing that, in fact, a vector bundle V and a section is a homomorphism from the trivial bundle to the vector bundle V. So you can replace those and consider arbitrary vector bundles, E1 and E2, holomorphic vector bundles, and a homomorphism from one to the other. And the same construction works. And there is a stability condition and some equations that emerge naturally and so on. And so another situation that even generalizes this even further has produced many works, and those are some, but there are many more in the literature. So to realize that, in fact, the most general SU2 equivariant holomorphic vector bundle on X cross P1 are in one-to-one correspondence with what we call chains over X, consisting of n vector bundles and homomorphism among them. And so, in fact, there are vortex equations for this situation and stability conditions which involve as many parameters as arrows in the chain. So in the particular case of triples, that involves one parameter, which is the situation of the vortex that I have been describing. So there are things, in fact, there's a vast generalization when you replace CP1 by other Flach varieties, and I won't get into that. But the reason I wanted to mention these generalizations, and in fact the power of vortices, abelian and non-abelian, is because this problem that looks rather, sort of academic, is in fact a very powerful tool to solve a problem in the theory of Higgs bundles, which is a very much object of interest for physicists and for geometers, and certainly I'm very interested in Higgs bundles. I've been working on them for the last 15 years. So again, you consider a compact Riemann surface, and a Higgs bundle is a pair consisting of a vector bundle, a holomorphic vector bundle. And now the Higgs field is not a section, but in fact a homomorphism from E to E tensor K, where K is a canonical line bundle. So Hitching introduced these objects almost 30 years ago. This looks like a joke, but next year, in 2 years, we'll have a conference celebrating 30 years of Higgs bundles. And very active area. So the moduli space of polystable Higgs bundles of rank R and degree D is a very interesting object. Has many geometric properties and so on.
We had to have conference celebrating instantons.
When would be?
1974.
Here you are. So this year.
Yeah.
Well, today is a celebration for instantons as well. 40 years of instantons and how useful they are. And so these moduli spaces in particular are homeomorphic to the moduli space of representations of the fundamental group of the surface, the character varieties. So that's a very sort of interesting object. And so to study the topology of, so people have been interested in the study of this moduli space of Higgs bundles for many reasons, related to Langland's duality and integrable systems and hyperkähler geometry, and in particular character varieties, so moduli space of representations of the fundamental group. And a very important tool that Hitching introduced is to do localization around the fixed points of a siesta action. So where the siesta action is multiplying the Higgs field by just lambda complex, non-zero complex number. And so it turns out that actually the fixed points of this are phi equals 0. So this is just a polystable bundle. Or if you want phi different than 0, then the vector bundle decomposes as a direct sum of vector bundles, and the Higgs field moves one piece to the other, tensor by K. So we realized that these are the moduli spaces of chains that I previously described. So that was the main motivation to study chains, the triples and chains, because as actually already, so the topology of the moduli of chains determines the topology of the moduli space of Higgs bundles, as already in the coprime case, when R, the rank and the degree are coprime, this is a smooth variety. And in fact, Hitching, in his first paper, as I said, well, I said in 16 will be 30 years, but the paper was submitted in 86. That's why we are celebrating the date of the submission. The submission.
2 years.
Sorry? Well, we can keep celebrating. Yes, but anyway. So this already Hitching, in fact, saw how abelian vortices appeared in the moduli space of rank 2 Higgs bundles, and in fact he was able to determine the topology of that thanks to the topology of the moduli space of a billion vortices, the symmetric product that had been computed by MacDonald long time before. And so in rank 3, one needs already the theory of triples and actually chains, right? And Peter Gotten computed the Poincaré polynomial. And more recently, for rank 4, in joint work with Heinloth and Schmidt, we computed the motive, which actually gives you the Poincaré, actually the Hodge polynomial and the Poincaré polynomials. And even more recently with, oh, actually, sorry, I mean, in fact, it's a work of me with Heinloth. Schmidt was collaborating here, not in this other thing. We solved the general problem. So we gave a recurrent formula to compute the motive, and therefore the Betti numbers and of the moduli space of Higgs bundles, and that was by studying the moduli space of non-abelian vortices. So that's some advertisement for the theory of non-abelian vortices and how useful they are. And also earlier, in fact, with Bratlow and Gotten, we computed homotopy groups, also for arbitrary R of these moduli spaces, always in the coprime situation. And I want to emphasize that, in fact, the parameters that appear in the vortex equations and the variation of the parameters is of central importance in solving the problem. So the parameter tau plays a crucial, and other parameters that in where you have chains of larger length plays a crucial role in the solution of the problem. Okay, so let's go to introduce some gravity in the sort of to get the gravitating vortices, and so am I going too fast? You have some questions so far before we get into more grave matters. Sorry?
You have about 25 minutes.
25 minutes, good.
Can you ever construct one?
Construct
A vortex.
depends what you mean. To find a solution,
Yeah.
an explicit solution. You know very well the answer. Okay.
I mean, surely algebraic geometers can tell you.
Well, in some particular situations, you know, like on elliptic curves and things like this, you can find explicit solutions, actually, right? But yeah, or do things with them like, you know, Fourier-Mukai transformations and things of that sort. But mostly in this story, like for instantons, you know, I mean, in instantons, of course, you have the. In fact, I started studying vortices because I wanted, inspired by the IDHM construction, Twistor methods, to find explicit solutions to the vortex equations. And in fact, your first question was very relevant because that was exactly what I was doing, considering that situation. But the Twistor methods were very complicated in that case, and I got discouraged. Right? So instead, you study the moduli space whole solutions and have very beautiful geometry and so on. But let's move to have gravity. And so I want to tell you about a theory that we call coupled Keller Young equations, which is a theory that involves the following. Before I get to gravitating vortices, so this involves a compact complex manifold of arbitrary dimension, M, and involves a holomorphic vector bundle over M. And here, these equations, what we call the coupled Keller-Young-Mills equations, are equations for a Keller metric on M and a Hermitian metric H on E. So as opposed to the Hermitian Young-Mills, where we fixed a metric on M and we looked for a Hermitian metric on E, here we do not fix the metric on M. So the two things are actually coupled. The Keller metric, I should have called it G on M, and a Hermitian metric H on E are coupled. And the set of equations that we get is the first one you can see is the Hermitian-Einstein equation, the Hermitian-Young-Mills equation as before. But now here we get another equation that actually intertwins the metric G on M. So I forgot to call the metric here G on M, and the metric H on the vector bundle, and the terms here are SG is the scalar curvature of G. And this is now, this term here is the trace of, this is an abbreviation for the curvature, wedge the curvature, is a 4 form, right? So this, the trace is then a 4 form of the manifold, which we then contract twice with the Keller form to get a function that we put against the scalar curvature. And we require that this is C. And so what are the other ingredients? So alpha, this alpha that appears here is a coupling constant, is a parameter, a positive parameter, right? And C is a real number that, this C here, that is determined by the topology. Similar as mu before was determined by the topology, here C is determined by the topology. So in fact, let me tell you what it is. Integrating the second, this second equation, we integrate the second equation, we realize that actually we obtain this relation that links this C that appear in the second equation to the degree of the tangent bundle of M and to the second chain character, right? And relates alpha. So that's explicit. Now, these equations have been introduced in the thesis of my former student Mario Garcia-Fernandez, and we wrote a paper with Luis Alvarez Consul, who was also a joint supervisor of Mario. And so we introduced these coupling equations, coupling a metric on the manifold and a metric on the vector bundle. And so this, yeah, sorry, I forgot to point out. These equations, they are not, so warning, physicists, these are not the physical coupling of gravity and Young-Mills, but they have a symplectic origin, however. And so let me explain the moment map interpretation of these equations. So for this, we fix a C-infinity, not holomorphic structure for the moment, but just we fix a complex vector bundle over M, right? And then fix the Hermitian metric, H on E, and a symplectic form on M. Right? So we actually take sort of this C-infinity bundle and a complex manifold, M, and we fix this, H and omega, and we consider the following infinite dimensional manifolds. So this is the manifold of set of all complex structures on M, right? And then actually I said we fix a complex, no, we don't fix, M is just a manifold, a real, even dimensional manifold. We don't compact, we don't fix the complex structure. So we consider all complex structures on M and all unitary connections on this Hermitian vector bundle. And so, and define inside here the pairs consisting of a complex structure and a connection that satisfy that A induces a holomorphic structure over Mj. So the first requirement is that J actually, these defined complex structures, they are integrable complex structures. And so A induces a holomorphic structure over this complex manifold. And this J and omega, actually Mj omega is a scalar. Okay, so this, so I claim that these two spaces actually have canonical symplectic structures, right? That one can construct. And in fact, on P, we can consider the restriction of a weighted sum of these symplectic structures, where we put here the alpha different than 0 is a real parameter. So we consider this, on this space of pairs, this symplectic structure that depends on alpha. Okay? So so this is the space. I said that there is these equations appear as symplectic moment maps. That is the space with symplectic structure. What is the group? And so the group is the following. Fujiki and Donaldson consider the group of Hamiltonian symplectomorphisms of the symplectic manifold M omega. Remember that we fixed omega. So this group H, and actually this group H acts symplectically on the space of all complex structures with the canonical symplectic structure that I said it has. And the moment map, they computed the moment map, and realized that for the complex structure on the manifold to be a zero of the moment map is exactly equivalent to the scalar curvature to be constant. So the constant scalar curvature condition appears as a moment map equation. And so in our case, we have to consider what we call the Hamiltonian extended gauge group. Is a group of automorphisms of this Hermitian vector bundle that cover, that induce on M a Hamiltonian symplectomorphism. So in other words, this group is an extension of the usual gauge group of automorphisms that cover the identity with the group, the Donaldson-Fujiki, the Fujiki-Donaldson group of Hamiltonian symplectomorphisms, right? So this is a group, is an extension of two groups. And so the claim is that this G tilde, this extended group, acts on J. It also acts on connections in the usual way. And in fact, it acts on this, it acts on the space of pairs. And there is a moment map, and being a zero of the moment map is exactly a solution to the coupled Young, Keller Young equations. So the Keller Young equations that I am telling you appear as moment map equations for the action of the extended gauge group, where extended question.
It is not the coupling to gravity, but there is something else that people were doing, like I think it's called the Bansky gravity or something. Instantons are coupled. So it's not really, and it appears actually in what's called 2,2 n equals 2 strings.
People have been, I don't know about this theory in particular, but people have been studying these things in many contexts, and on Riemannian for manifolds and other situations. I mean, but we sort of wanted a situation in the context of Keller geometry. And what naturally comes in the context of Keller geometry is this. Is moment map equations dictate somehow what are the natural equations. Once you have the natural symplectic structures, right? So, we were wondering from the beginning what was the relation with other theories that physicists have been studying.
This is the one, because
okay.
about instanton equations. Moment, also written as writing is a moment.
I see.
Right? Then it's a natural way to this complex introduce the.
So the base manifold is symplectic also in that situation. Well, I'd love to learn more about that. Perhaps that we'll see a surprising connection to physics, to physics theory, but in a moment. Okay. So these equations actually, in fact, for alpha bigger than 0, this space of pairs has a canonical J tilde invariant Keller structure, and moreover, the moduli space of solutions to the coupled equations, which is solutions to the coupled equations modulo, this extended gauge group is scalar, when alpha is bigger than 0. So remarks that we want to make is that you notice that we recover the Hermitian Young-Mills equations. So while this equation is the Donaldson, the constant scalar curvature condition that is the base of the theory of Donaldson, Tian, and Yau gets deformed. Right? So this theory that we are presenting here combines somehow the Hermitian Young-Mills theory with the theory of constant scalar curvature of Donaldson, Tian, Yau, and others. Okay? And so notice, so then the equations actually decoupled when the complex dimension is 1. On Riemann surfaces, these equations actually decouple simply because this term is 0. There are no 4 forms on Riemann surfaces. Okay, that's one of the thing. The other thing I want to mention is that these are not only appear as moment map equations, but they are also solutions to so minima of a certain something we call Calabi-Young-Mills functional. This is a natural functional that for which these are actually minima. And so the program that we established was to study the existence of solutions, and we realized that, of course, if you think how difficult the problem of Donaldson, Tian, Yau has been and is, well, this is an even more difficult problem. Okay, and in our paper we gave a conjecture in terms of geodesic stability. Let's see, that. Let me tell you something about this. But I will go a bit quickly because I want to get to the gravitating vortices. But so this is what, so to formulate this conjecture, we want a Hitching-Kobayashi correspondence to these things, right? Like the usual Hermitian Young mills or the Donaldson-Tian-Yau theory. And so, but we need a stability condition. And so here is a stability condition that we get inspired by the theory of Donaldson and Tian-Yau. So this is called geodesic stability. And for this, even get now a different point of view where we actually fix the cohomology class of the manifold M, the two cohomology class, and we also fix the pair complex structure and the connection. This is the same as actually giving a complex structure on the tangent bundle of the vector bundle B. And then what we look for, we vary actually in pairs consisting of the symplectic form, omega, and Hermitian metrics on the bundle. And these pairs, we call small b. They have to require that omega is in the fixed class that we have put here, and that such that mj omega is scalar, and H is a Hermitian metric. So it's a very natural sort of thing. So we fix this class, and we fix a pair, this, and we vary here. And that space, so the important thing to establish geodesic stability is that the space in question is a symmetric space. So it has a canonical affine connection, which in fact has, is torsion-free, and it has this condition of the curvature of the connection. So this is what you need to actually, for example, let me just mention, if there is no bundle, and so we go back to the theory of Donaldson, then in fact this symmetric space is Riemannian, and with the Mabuchi metric that was also rediscovered by Donaldson and Stephen Sims. But otherwise, this is not Riemannian. That's another difficulty in the problem. But it has this connection. And with this connection, we can actually define geodesics in that space. And so for each B, remember this B here was actually a symplectic form and a Hermitian metric. And this is what we needed to define, our extended gauge group, and also our space that of pairs, right? So we had Hamiltonian action that I was mentioning before, and the moment map, and so we can define a one form on this. This is very technical, so I'll go quickly. And don't worry. But the main point is we define a one form here, using basically the moment map that I told you that existed. And then we say that a complex structure I on the tangent bundle, which is the same as a connection and a complex structure on the manifold, is geodesically stable if the limit of, if this limit here, we put this one form against, we take any non-constant geodesic ray, right, is this limit is actually bigger than 0 for stability and semi-stability bigger or equal than 0. So some condition that makes use of this affine connection that one has. And so the conjecture, rough conjecture that we have, is that the existence of solutions to the couple Keller Young Mills equations is equivalent to this I being geodesically stable. So it's very similar to the Donaldson Tian-Yau theory. But the fact is that this geodesic stability is extremely difficult condition to check. And so what we then try to do is to try to test this condition in the simplest possible cases. And so the one thing one thinks is, oh, let's go on Riemann surfaces. But what happens on Riemann surfaces, as I told you before, is that the equation decoupled. So there is nothing there. However, we know from our previous experience that we can obtain something on Riemann surfaces if we simply do a dimensional reduction from x cross P1 to the Riemann surface x. And this is exactly what I'm going to do. So we are going to try to obtain, I mean, this is what Witten was doing when he originally was studying vortices on the hyperbolic plane. He was just trying to study instantons, but study instantons that were invariant under SU2, right? And so that's how he got the vortices. So that's what we try to do. And so here is how we get to the gravitating vortices. And what is this? So X is a compact Riemann surface. And then, as before, I consider L to be a holomorphic line bundle, right? And a section. So this is a general setup. And as we saw before, we can construct a rank 2 SU2 invariant holomorphic vector bundle over X cross P1. This is as we did before. Now, this is the vector bundle extension. Now, here's the main fact. The fact is the following. A SU2 invariant, because this vector bundle has a structure of the action of SU2 and it's invariant, so we can look for invariant solutions to the coupled Keller Young equations. So an SU2 invariant solution to the coupled Keller Young equations on this vector bundle on X cross P1 is equivalent to the following set of equations. It's equivalent to solving, it's equivalent to solving for a metric G on X and a Hermitian metric H, I should have said on L, excuse me, this is an L, typo, on the line bundle, such that we get the vortex equations that we know, and then we get another equation here that couples the metric on X and the metric on L. So, and then there are a number of parameters like tau, and there is alpha, and there is C. And so what are, let me recall these parameters. Tau is like the vortex equation, is a positive real number. Alpha is also a real parameter. And C is determined by the topology, as it was, but let me tell you exactly what it is. So by integrating the first equation is actually the familiar vortex equation. By integrating this equation, we did that already before, right? But by integrating that, we obtain this relation, right, here, that links the degree of L to this. And then, because of the, if we look at the second equation, and we now observe that the integral of this is 0, and that the integral of the scalar curvature is linked to the Euler characteristic of X in this way and the volume, then we obtain the following relation. The C is determined by this, is determined in terms of the topology and the parameters alpha and tau, right?
Is it compatible with the Riemann structure?
Yes.
The Riemann structure?
Yes, it has to be in the. Actually, well, let me. Actually, now that you say this. I don't know actually. I would a priori no, I suppose it does. Yeah. No, it is. Yes. But I have a little doubt. But okay, we can discuss this maybe later. But let me see. I don't know if a priori we impose that, or is actually no. I'm not sure. A priori is. I don't see at the moment why that has to be the case. But here is first 2 minutes. Okay. So here is what first thing, that if this C is 0, then X is actually has to be CP1. So this forces the topology, and so we obtained. The vanishing of this constant is just forces the Riemann surface to be P1, and so the striking fact for us was to find out that precisely in this situation, our gravitating vortex equations actually had been studied in the literature, and in fact appeared in a very relevant context in the physics of cosmic strings. And in particular, so we see that when C is equal to 0, our gravitating vortices are in fact solutions to, are in fact equivalent to what is called cosmic strings. And cosmic strings are, or sometimes called topological defects, are solutions to the coupled Abelian-Einstein-Higgs equations on the product of R11 cross X. So independent of these variables in R11, right? And so So this is a coupling of gravity with the theory of superconductivity, where alpha is nothing but, in fact, 2 pi, the universal gravitation constant. And so we were very surprised to see that indeed these equations have been studied, and there is a substantial physics literature in it, Compton and Gibbons, and Brooke and Young, in particular has studied these things. So we then makes us believe that our equations, our coupled Keller-Young equations, are of physical content, because we do obtain these equations. And in fact, this constancy is morally the minus the cosmological constant. So we can actually come back to our general equations and write them a la Kasdan-Warner by fixing metrics on x and L and just looking for functions u and f. That so if you're a PD person, you would like to see equations like this. And so this, whoever does PDs realizes they are very difficult equations, right? Not like the Kasdan-Warner, but much more difficult. And however, one sees that in particular, if C is actually 0, so then we get that this is constant, and from there we get u in terms of this, and we can plug u in this other equation, and we can study this equation. It's an easier equation, and this was done by Young precisely, and he obtained the following theorem. That so Young obtained the following theorem that that if you take big N to be the degree of the line bundle, and you take a divisor, an effective divisor on P1, which is what corresponds, the zeros of phi define a divisor, right? So this is a divisor. But such that this condition is satisfied, right? And N is less than tau. So he proved that this admits a solution to the gravitating vortex equations if Ni is smaller than half of N big N over 2 for all I, and also that there exists a solution that has N times a point and N times the antipodal point if small n is exactly half of this. So what was so he applies a continuity method. Can I have maybe another couple of minutes, please? Because I want to get to the point. So he applies a continuity method to the Kasdan-Warner type equations in the case of C equals 0. But the striking fact was to realize, sort of for us, that the condition that Young's actually gives is precisely the condition that corresponds to Mumford GIT stability for the natural action of SL2C on the symmetric product of P1. This is precisely for many people here, this familiar space of a billion vortices on P1 is a symmetric product, right? So, so that condition is exactly the GIT stability condition. In fact, this first condition that he wrote is corresponding to the divisor being GIT stable, and the other one, which correspond to these special solutions, correspond to a strictly polystable, right? So this makes it to make several conjectures, and so we are conjectured that the converse. So Young showed that that was sufficient to have solutions. So we conjectured that this is actually necessary and sufficient. So that in fact there is a correspondence between being stable in this sense and having solutions to the gravitating vortex equations. And we wanted to give a geometric proof of this correspondence. Then that the moduli space of cosmic strengths in that particular case is in fact this GIT quotient, right? And that moreover, and this was our motivation, we wanted to get a grasp of what is geodesic stability meant, at least in this. This is about the simplest toy model you can have. And so that the geodesic stability of this bundle, SU2 invariant, because we have this action, should be equivalent precisely to this GIT stability condition. Now, to finish, some final comments. We have made, I promised Nuno that we have made progress on this. We haven't quite completed the program, but we have made very substantial progress in the proof by using precisely not what we suspected, an algebraic approach using balanced metrics like Donaldson, but actually making use of this geodesic equation. So using this geodesic stability applied to this situation. But it turns out that it's very hard even for Riemann surfaces, but Donaldson, he studied, we were very lucky that he studied the geodesic equation for the space of Keller matrix precisely on CP1. It was a study, solved by Donaldson in some cases, not all. So we don't get actually, even for CP1, so if, Donaldson did part of the work for the technical work, but it doesn't solve the problem actually. So it's very difficult. And so the geodesic equation on the space of Keller matrix is related to the complex Monge-Ampere equation, which has been a lot of activity. And we realized that actually the study of our problem is links to what you could have asked also as what is the simplest situation you may study for this coupled Keller Young equations, which is not to do dimensional reduction of a rank 2, but to study actually the problem on line bundles, so the abelian situation, right? And so this is precisely what we are doing also. And in the abelian situation, we do this. We take a manifold, complex algebraic variety, polarized variety of any dimension, and E is just actually the kth power of the line bundle. And so there, our equation reduced to something much simpler, right? This sort of makes sense to study because they can, one can have solution on manifolds which do not admit a constant scalar curvature matrix by the theory of Donaldson. We have actually evidence of this phenomenon. So I mentioned this other problem on line bundles because it is related to our problem technically. So the geodesic stability, which is the main analytic tool, in both cases is very similar. So we hope to make progress. We haven't completely given the geometric proof, but we have enough evidence actually deforming some of the Young solutions using this geodesic stability. And hopefully this will provide a proof of the conjecture. But what we know clearly is that even in the simplest case, this is a very difficult problem. So I should stop here.
Question, please.
So for the elliptic curve, this is even more difficult than P1, or have you moved to that?
Well, okay. So I said before that there was this constant C, right, and C equals 0, which is the easy to handle analytically, forces the topology to be genus 0, right? So we're on CP1, right? Now, so we would like to study these equations for any genus, and in particular for on an elliptic curve. So, but we don't know. It should be even more complicated, I guess. Yeah.
So we like consider like on the plane, like in the tops type situation.
Well, that is precisely the situation that that Compton, and Gibbons and in fact Young himself studied, right? Also, and that is the one that links to the cosmic strings, right? And CP1 also links to the cosmic strings. For higher genus, actually, we don't know the relation with there's anything cosmic strings. If it was on a constant, sort of lambda being given a 0, right? Sort of, but yeah, so that is the analysis for that situation has been done, right? On compact Riemann surfaces, the simplest case is CP1, and it's very difficult.
If you had taken X cross P1 and not imposed the SU2 invariance, how complicated? I mean, we went by so quickly, it's hard to actually see what the SU2 invariance was given.
Well, if you consider X cross P1 and you don't impose the invariance under SU2, then you don't have you of course you have this still this extension, right? But then there are more general bundles that you should consider, and then you basically cannot perform dimensional reduction on them. You obtain other things, but they do not give you anything on X, right?
But you had two sets of equations that didn't require dimensional reduction. I'm just trying to understand the structure of those.
No, all those equations, the equations that I got going from the Hermitian Young-Mills or the Keller, the couple situation, required invariance. It was thanks to the invariance that we could get precisely to these equations. Otherwise, you don't get dimensional reduction. This is the crucial thing about dimensional reduction also in physics.
A particular case of solutions on the sphere would be those which are invariant under rotations.
Right. So this is what. Yeah. This is what.
Check the stability conditions in that case.
Even that case is quite complicated. And in fact, what we did was to realize that this is a toric situation, right? Yeah. And we used sort of the natural coordinates there, right? And the geodesic equation in that situation, the geodesic equation, even there, we expect it to be actually a very easy ODE, but it is not, actually. So, yeah, even that situation is a bit, yeah, that was, there are ways to handle sort of, getting these geodesic equations are not too bad, but not as simple as we thought. And in particular, we thought that in that case, it would be very simple. Basically, what Donaldson does the job for us. But he doesn't solve the equations for everything. So I think something is getting nervous that we missed the bus, huh?
Yeah, I don't want you to miss the bus.
Thank you.
That's a good guy.
Thank you.